We now consider quasi-birth and death processes. For a regular birth and death process, we had a rate matrix Q, which was tridiagonal. We still have, with quasi-birth and death processes, we still have a rate matrix Q, which is partly tridiagonal. And when I say partly tridiagonal, I mean that the entries that you see in the matrix Q are not simple numbers, they are in fact matrices. So Q00 here is a matrix. Q01 is a matrix. Q10 is a matrix. Q11 is a matrix. Q12 is a matrix, etc. Now, the rate matrix Q does still satisfy the fact that all the entries are non-negative except for the diagonal, and the diagonal is chosen so that the rows of Q will sum to 1. Okay, so let's look at a special type of birth and death, quasi-birth and death process. So we're going to assume that there are two servers. We have two types of customer, long or short. The arrival rate of customers is lambda, and we'll break that lambda up into two parts, lambda 1 and lambda 2. Lambda 1 would be the short, the customers that require a short amount of service. Lambda 2 would be the customers that require a longer amount of service. The service rates are mu1 and mu2. Mu1 would be the rate for the customers that require a short amount of service. Mu2 would be the rate for customers that require a longer type of service. The states of our system are 0, meaning there are 0 customers in the system. The state could consist of a pair, 1, 0, which means there is 1 short customer, 0 long customers. 0, 1, which means there are 0 short customers, 1 long customer. 2, 0, remember there are 2 servers, so 2 short customers, 1 short and 1 long, or 2 long service required customers. When we get to the next stage, which has 3 customers, since there are only 2 servers, we could have both servers are serving a short customer, and there's 1 customer waiting. We don't know what kind it is. We could have 1 short customer in service, 1 long customer in service, 1 waiting, and again, we don't know what kind it is. 0 short, 2 long, and 1 waiting. We don't know what kind. Let's summarize what we just said. The states of the system have the following appearance. 0 means the system is empty. 1, 0 means 1 short customer. 0, 1 means 1 long customer. 2, 0, 2 short. 1, 1, 1 short, 1 long. 0, 2, both long. So the first entry is the number of short, and the second entry is the number of long customers. We could also get up to a triple where we have 3 customers in the system, 2 short and 1 waiting. We're not going to specify what that waiting one is yet. 1 short, 1 long, and 1 waiting. 0 short, 2 long, and 1 waiting. Now, one way to look at this is to say that the arrival rate is lambda, and once an arrival enters into service with probability P, it will be a type 1 customer, so that will correspond to the rate lambda 1. With probability 1 minus P, the customer will be a long customer. So lambda times 1 minus P would be the arrival rate of the long customers, lambda 2. So the lambda that we're talking about here is the sum of the lambda 1 short arrival rate, lambda 2 long arrival rate. We can make a flow diagram of the following type, and I'm going to break it up into two diagrams. We could put them into one, but it would get very cluttered. So the top diagram would show the arrivals. The lower diagram would show the service completions. So if we have 0 customers, we will either get an arrival of type 1, it will go to the short list, or an arrival of type 2, it will go to the long list. If we have 1 customer in the system that is short, we could move to 2 customers that are both short customers if there's an arrival of another short one. We could move to the 1-1 category if a type 2 customer arrives. From 0-1, so we have 1 long already, we could end up with 2 long, or 1 long and 1 short, rates lambda 1 and lambda 2. From 2-0, so we have 2 short customers, the arrival rate is lambda, and we will end up with 2 short, 0 long, and 1 waiting. We don't know what that 1 waiting is, whether it's short or long, and we will not know until it actually enters service. Then we will classify it. Okay, so those are the arrivals. Service completion. Let's look at this second diagram. From 1-0, a service completion at rate mu1 will bring us down to 0. From 0-1, a service completion at rate mu2 will bring us down to 0. 2-0 can go to 1-0, double the rate because we have 2 short customers being served. 1-1 could either go to 1-0 or 0-1, and it depends on whether the second customer is served or the short customer is served, the long customer is served, or the short customer is served. Let's back off one more stage. Suppose we had 2 short, 0 long, and 1 waiting. And if there's a completion, it has to be a type mu1, so a short completion. So that's, and there's 2 of them, so that's 2 mu1. And we will, so 2-0-1 will go to 2-0. That means the extra customer must go to the short category. And the probability that happens is P. So now we have 2 mu1 P. Similarly, if that extra customer that is waiting is in fact a long customer, then we'll go to state 1-1, and that happens with rate 2 mu1 1 minus P. Okay, so we have those type. We have a special case if we're in the 1-1-1 case. That's a little bit different. We could have a short customer completion. We could have a long customer completion. The extra customer could be short or it could be long. So suppose the short customer leaves. So that would happen with rate mu1. And this waiting customer is in fact a short. So that would happen with rate P. So if we look at A here, what happens? I guess the second customer has to leave rate mu2, and the extra customer has to be short, probability P. So that's what A corresponds to. The B is, again, more complicated. This 1, 1, 1 will go to a pair 1, 1 if you have a short completion and the extra customer is short, a long completion and the extra customer is long. And so B will be given by this expression here, mu1p plus mu2 times 1 minus p. And similarly for the entry C, which would stand for mu1 times 1 minus p. We can take all those rates that we've been discussing and get a rate matrix. So here is our rate matrix Q. Here are our states 0, 1, 0, 0, 1, 2, 0, 1, 1, 0, 2, 2, 0, 1, 1, 1, 1, 0, 2, 1, and it keeps on going. The next one would be 2, 0, 2, 1, 1, 2, 0, 2, 2. We can fill in all the rates. The diagonal, as usual, is chosen. The entries are chosen so that the rows sum to 1. If we're in state 0, we either have a type 1 arrival or a type 2 arrival. From state 1, 0 or 0, 1, we will have type 1 arrivals or type 2 arrivals. If we're in state 2, 0, we don't classify whether an arrival is type 1 or type 2. We just have an overall arrival lambda that will be broken up into lambda 1 plus lambda 2, but we'll just leave it as a lambda here. We have service completions, and we have all those entries that we showed on the state diagram. Now, some of these things are fairly interesting. For example, we have a block over here. I'm in the upper left-hand corner and in the lower right-hand corner. And that's a block of, it's a diagonal lambda matrix. And that will be the arrival rate matrix, the submatrix for the arrival matrix. So it's always going to have this diagonal lambda times the identity. We also have a 3 by 3 matrix here, which shows the type of decrease from one state to another, or one classification of states to another. And this same matrix, this same submatrix, will repeat itself as we move down the diagonal. And as before, the diagonal, the true diagonal is chosen so the entries, so that the rows will sum to 0. And here's the summary of the Q matrix, and I'm going to actually specify what these various Qij are, and we'll see that there is a pattern that is going to repeat.